Oh my God, there's my. I'm like so sick this semester. I'm not so unsure. I think it was hard to get up.
Okay, so we are going to study how to do a air standard analysis of reciprocating internal combustion engines. So there are several assumptions that we need to make. The first one is we are going to assume that the working gas is air and it's going to behave like an ideal gas. So we can use a ideal gas equation, and this combustion process can be replaced by heat transfer from an external source. So that's going to be Q in, and we are going to neglect intake or and exhaust processes, and the heat transfer in and out can be assumed to be constant volume heat transfer. So there should be Q in and Q out. And we assume that all processes are internally reversible, which means that entropy S remains constant. So the change of S remains constant. And one special case is called cold air standard analysis. If we use this cold air standard analysis, we can use constant specific heat. So in this case, specific heat, CV and CP, CV and CP, they are constant. So there is just air standard analysis and there is a cold air standard analysis. So if we just use air standard analysis, we cannot use specific heat. But if we make another assumption that is cold air standard analysis, then we can use specific heat. So when you solve a problem in this chapter, you need to make sure that if it is just standard air standard analysis or cold air standard analysis, because the way to determine specific internal energy, specific enthalpy are going to be different. One, we cannot use specific heat. The other, we are going to use specific heat. So if we cannot use the specific heat, we are going to use a table to determine their thermal properties. Okay? So there are two cycles that we are going to study. The first one is Otto cycle. The other one is diesel cycle. So let's start with Otto cycle first. So this is how this air standard Otto cycle looks like. So we have the number one is going to be the starting point. So we have a compression stroke. So that's going to be isentropic compression. So there are four processes. The compression stroke is going to be isentropic compression. That means entropy S remains constant. And process 2 to 3 is going to be constant volume heat addition. So there is Q in and volume remains constant. V2 is the same as V3. And isentropic expansion, that's when we produce power and specific entropy S remains constant. And finally, constant volume heat rejection from the system. So we have Q out and volume remains constant. V4 is V1. So when we study this Otto cycle, we are going to use two property diagrams. The first one is PV diagram. The other one is TS diagram. And based on the information provided here, you can complete this PV and TS diagram. The first one, let's start from here, number 1. And here, number 1. The first process is isentropic compression. So this is a compression process. Therefore, volume is going to decrease, this volume, and pressure is going to increase. So this way. On this TS diagram, isentropic compression, so entropy S remains constant. So entropy S, the horizontal axis is entropy, so S1 is the same as S2. That means process 1 to 2 is going to be either going upward or downward. Since it is a compression process, temperature should go up. So, oops. Process 1 to 2 is going to be this one here. So here is number 2, and here's number 2. And the next process is constant volume heat addition. So heat is going to be added when volume remains constant. Volume is the horizontal axis of this PV diagram, so V2 should be the same as V3. And it's going to be either going upward or downward. However, there's a heat is added, therefore pressure should go up. So this way. So there's number 3. On this TS diagram, heat is added, therefore temperature should go up. And heat is a waste form of energy, therefore the total entropy should increase. So this way. So process 2 to 3 is going to be going up like this. So there's number 3. And we have an isentropic expansion, process 3 to 4. So this is an expansion process, therefore volume should increase, pressure should decrease. So process 3 to 4 gonna be here. On this TS diagram, entropy S should remain constant. S3 should be the same as S4, and it's an expansion process, temperature should decrease, therefore this way. So there's number 4 and number 4. And finally, process 4 to 1 is constant volume heat rejection. So it's going to be constant volume. V4 should be the same as V1, and heat is removed from the air, therefore pressure goes down this way. And on this TS diagram, heat is removed, therefore temperature goes down, and heat is waste form of energy. So when you remove heat, entropy goes down. So this way. So there's a PV diagram and TS diagram. And the same as Theta 4 vapor power cycle, the enclosed area represents the network developed. Okay? So that's how you make PV and TS diagram. Whenever you have air standard Otto cycle or diesel cycle, you need to learn how you need to, the first thing you have to do is make TV and TS diagram. Then let's try energy balance equation. By the way, previously we studied one of the main thermodynamic property is going to be compression ratio. Oh, no, I'm sorry, it's not a thermodynamic property. It's a parameter of this Otto cycle. It's called compression ratio. This compression ratio can be determined by this is the volume when the piston is at the top dead center. And this is the volume when the piston is at the bottom dead center. So you can understand this way. So here is the piston. And there's a spark plug. And piston is moving between here and here. So this one is moving back and forth. So the volume of the air is going to be this one when the piston is at the top dead center. And the volume of the piston, the air is this much when the piston is at the bottom dead center. By the way, just for your information, we are not studying this engine. We are just studying how to apply thermodynamic laws in different applications. In this case, it just happened to be air standard Otto cycle. So let's apply energy balance equation. When you study energy balance equation, there are two energy balance equations. One is for a closed system, and the other one is for an open system. We have two different energy balance equations. So when you look at this one, is it a closed system or an open system? How do we know whether it is closed or open? We are going to assume that when we have a closed system, mass is constant. When we have an open system, mass is not constant because we have an inlet or an exit. So the volume, the mass, the air in this piston cylinder device, mass of the air does not change. So this is a closed system. So when you have a closed system, what is the energy balance equation? The energy balance equation is Q in plus W in minus Q out minus W out is going to be mass times U2 minus U1 plus moving boundary work. That is the general energy balance equation. Then if it is constant volume process, then the right-hand side is going to be mass times U2 minus U1. If it is constant pressure process, the right-hand side is going to be mass times H2 minus H1. That is the general energy balance equation for a closed system. So in this case, we have constant volume process between 2 and 3, constant volume process between 1 and 4. So we can use this one for this constant volume process, and this one for isentropic process. So between 1 and 2 is going to be this one, between 2 and 3, this one, between 3 and 4, this one, between 4 and 1, this one, okay? So based on that, let's find the energy balance equation. The first one, between 1 and 2. So what happens between 1 and 2? Oops, more space. Between 1 and 2, it's going to be isentropic compression. So it's going to be isentropic compression. Entropy remains constant. There, in order to have a compression process, there should be work from outside done on the system. So we can use this equation. When we have an isentropic compression process, we can neglect Q in or Q out, because when there is a heat transfer, entropy should change. However, entropy remains constant, so we can neglect Q in and Q out. What about any external work? We have compression work, but the compression work is going to be here. So W in and W out, you can neglect them too. So for process 1 to 2, we can say M U2 minus U1 is going to be moving boundary work, but there is more than one moving boundary work. So let's say this moving boundary work WB is going to be the work between process 1 to 2. So I'm going to say W1, 2. I don't know why I wrote here. W1, 2. So this is the energy balance equation for process 1 to 2. This one. What about process 2 to 3? 2 to 3, it is a constant volume process, so we can use this equation. And in this case, process 2 to 3, there is a heat addition. So heat is added between 2 and 3. So we have Q in, and this one, we can neglect the other 3. So the energy balance equation is going to be Q in, but it is between 2 and 3. So let's say Q23 is going to be mass times U2 minus U1. This is process from 2 to 3. So we can say U3 minus U2. So that is the energy balance equation between 2 and 3. Then between 3 and 4, 3 and 4 is a isentropic expansion. So we are going to use this equation. We can neglect the left-hand side. So we have mass times U2 minus U1. However, this time it is between 3 and 4. So we can say mass times U4 minus U3. It's going to be moving boundary work plus W3 to 4 is going to be 0. So if you move this one to the other side, we can rewrite this one as W3 to 4 is going to be mass times U3 minus U4. And the last one is constant volume heat rejection. So in this case, we have Q out and this one. So let me write it here. Minus Q out. By the way, Q out is between 4 and 1. So I'm going to say Q4 and 1 is going to be mass times U2 minus U1. It is between 4 to 1. So I can say mass times U1 minus U4. So let's remove this negative sign. So it's going to be Q41 is going to be mass times U4 minus U1. So we have 1, 2, 3, and 4 energy balance equations. So whenever we have an Otto cycle, these are the 4 energy balance equations we can use to determine, let's say, work or heat. Then, how can we determine the thermal efficiency? So let's evaluate the performance of this cycle. So the efficiency can be determined by desired output over required input. That's what we studied in chapter 5. And what is desired output when we have a heat engine in chapter 5. So chapter 5, heat engine, W net divided by Q in. That was how we determined thermal efficiency in chapter 5. So what is W net? The work produced between 3 and 4 minus the work consumed between 1 and 2, because 3 to 4 is the expansion process when we produce work, and process 1 to 2 is the compression process we consume work. So this W net is going to be W 3 to 4 minus W 1 to 2. Then where is the heat transfer in? Heat transfer in between 2 and 3. So Q 2 3 is the heat transfer into the cycle. So what is W3 to 4? W3 to 4 is here, mass times U3 minus U4, mass times U3 minus U4, and what is W1 to 2 is here, mass times U2 minus U1, mass times U2 minus U1 divided by Q23. It's going to be mass times U3 minus U2, mass times U3 minus U2. So we can cancel mass, then this is how we determine the thermal efficiency. So this is how we do air standard analysis for this Otto cycle. So if you see a problem in your final exam, let's say that there is an Otto cycle, this is the pressure before the compression process, this is the temperature after the expansion process. So there will be some properties provided in this, in the problem statement. Then based on these energy balance equations and this thermal efficiency and this compression ratio, then you will be able to determine, the anything. So this is the summary for Otto cycle. Any question? By the way, you can use the formula sheet in the final exam, so you don't have to memorize them. Just the practice, the what I did from the beginning to the end a few times, so you can understand, the how to make this slide. So once you are able to to do them, then you should be fine solving any problem. The rest of them is going to be just find the property in, let's say, find the property such as U1, U2, U3, U4 from a property table. That's all you're going to do. Okay. So before we going forward, let's learn how we can, to improve the performance of this Otto cycle. So basically, the enclosed area represents the power the work we produce. So if we increase the enclosed area, that's one way to improve this cycle. So how can you improve them? So this is the original design. How can you improve this one? The simplest way is going to be make it longer. Make this cylinder longer than this one and move this top dead center to the left. So let's say up to here. So if you move this top dead center up to here, then the new number 2 and 3 is going to be placed right here, 2, 3. So we can increase this much work added to the cycle. Similarly, on this TS diagram, number 2 moves this way, number 3 moves this way. Similarly, number 2 moves this way, number 3 moves this way. So we can add this much work. So the simplest way to improve the performance of this reciprocating internal combustion engine is going to be make this one longer so we can have more compression. In other words, we can improve the compression ratio. So this one determines compression ratio because the compression ratio is this volume divided by this volume. So V1 divided by V2. So the compression ratio R is going to be V1 divided by V2. Or you can say V4 divided by V3 because V1 is the same as V4 and V2 is the same as V3. So this compression ratio is the key to improve the performance of this Otto cycle. And that's how that we came up with the idea diesel cycle. Because if you just keep increasing the compression ratio, the air-fuel mixture is going to the self-ignite before this piston reaches the top dead center. So instead of compressing air-fuel mixture, let's compress only air and then inject fuel later. That is diesel cycle. Trying to increase this compression ratio. Because there's a limit for the compression ratio in the Otto cycle because of this spark plug. Okay? So that's everything for Otto cycle. And before we study diesel cycle, let's practice one problem together. So you will understand, how to solve problem related to air standard Otto cycle. By the way, any question about this air standard Otto cycle? The concept is very simple. We only have four processes, consist of simple isentropic compression, isentropic expansion, and constant volume heat addition, constant volume heat rejection. Based on that, we came up with these four energy balance equation. Four, not this one. 1, 2, 3, 4. And based on that, we calculated the thermal efficiency that also, that consists of U1, U2, U3, U4. And finally, there's one parameter which is related to the performance of this Otto cycle, that is this compression ratio, can be determined by that equation. So there are not many equations here. We are going to use them to solve a problem. So basically, what you can expect is whenever you see an Otto cycle, you need to determine U1, U2, U3, U4 first. Then you can start analyzing this cycle. Okay? So let's look at this problem. At the beginning of the compression process of an air standard Otto cycle, pressure is P1 is 1 bar, T1 is 290 Kelvin, V1 is 400 centimeter cube. The maximum temperature in the cycle is 2200 Kelvin, and the compression ratio is 8. So we want to determine the heat addition, the net work, the thermal efficiency, and the mean effective pressure. So let's do that. So when you see air standard Otto cycle, the first thing that we need to do is to make PV and TS diagram. So let me do exactly, what we have to do. So PS diagram, a PV diagram first, and TS diagram next. And as we saw here, the first process 1 to 2, is an isentropic compression. From 1 to 2, isentropic compression. 1 to 2. On this TS diagram, isentropic compression. So we have a vertical line because entropy S should remain constant. So 1 to 2. In this case, S1 is the same as S2. And then we have constant volume heat addition. So constant volume heat addition. So the volume should be constant. V2 should be the same as V3. So there's number 3. And constant volume heat addition, number 3. And isentropic expansion. Entropy remains constant. So S3 is the same as S4. So there's number 4, isentropic expansion. Then number 4. And finally, the cycle is going to be completed by constant volume heat rejection. Constant volume V1 is the same as V4. Constant volume heat rejection, this way. So we just made PV and TS diagram. Then what's next? Let's read the problem statement. P1 is 1 bar. So at this time, P1 is 1 bar. P1 is 290 Kelvin. And V1 is 400 centimeter cube. So this one we can say 400 centimeter cube. And the maximum temperature, where is the maximum temperature? The temperature is the vertical axis on this TS diagram. T3 is the maximum temperature. So T3 is 2200 Kelvin. The compression ratio is 8. So V2 can be found. Where's V2? It's going to be 400 divided by 8. What is 400 divided by 8? Yeah, 50 centimeter cube. So let's solve this problem. We need to determine U1, U2, U3, U4. So that's what we are going to do first. We are going to determine U1, U2, U3, and U4. And what is the working gas in the system? Air, ideal gas, air. So there's a table for ideal gas of air. Table A22. So if you see table A22, ideal gas properties of air. So we are going to find table A22. Ideal gas properties of air. And what is the temperature? T1. T1 is 290. So let's find 290. It's right here, 290. Let me zoom in for you. Not that bright. Okay. So at 290, U is going to be 206.91. So you can directly find specific internal energy U when you know the temperature. So 206.91. Kilojoule per kilogram. And we know one more temperature, T3, 2200. Oops. T3, 2200. So let's find U3 from the same table. Where is 2200? Not here. So let's go to the next slide. Next page. 2200 is here. And internal energy U is going to be this number, 1872.4. Am I right? Yeah. 1872.4 kilojoule per kilogram. Now the problem is U2 and U4. How can you find U2 and U4? There's one information we have, which is between 1 and 2, it's going to be isentropic process. In chapter 6, we studied how, the several equations for isentropic process. And one of them is, you may remember, when you have a variable constant specific heat, T2 over T1 was T2 over P1 to the power of kappa minus 1 over kappa, something like that, that we saw in chapter 6. But that's for constant specific heat. But this time, we don't have constant specific heat. Then we can use this equation. V2 over V1 is the same as VR2 over VR1. So this is okay when you have isentropic process. There's one more. P2 over P1 is PR2 over PR1. That is also valid when you have an isentropic process. So we are going to use one of these to determine the properties at state number 2. So how can we do that? We know V1 is 400, V2 is 50, so we can determine V2 over V1. That V2 over V1 is V2 over V1 is the compression ratio 8. Then we can say this is also the same as VR2 over VR1. So this is the equation that we are going to use. Then what is VR? VR can be found from the same table, table 822. If you go here, this is table 822. There's a PR, and this one is VR. So what is VR at state number 1? At state number 1, the temperature was 290, so you can find VR, 676.1. So at 290 Kelvin, VR is 676.1. So this number, 676.1, is VR1, 676 what am I doing? 676.1. Then from here, you can determine I made a mistake. So V2 over V1, V2 is only 50, V1 is 400. So that is not 8, that is 1 over 8, right? My mistake. 1 over 8. So 1 over 8 is VR2 over 676. Can you determine VR2? Yes, you can determine VR2. So if you solve this VR2, we get 84.5125. Once you know VR2, you can find this VR2 on the same table. So VR2 is 84. So let's find 84. There's not here. 84 is between these two numbers. 84 is between these two numbers. So can you determine internal energy U at the same VR2? Yes. So you can do linear interpolation between these two numbers and to determine U2. So from here, you can determine U2. When you do, U2 is going to be 475.11. U2 is going to be 475.11 kilojoule per kilogram. How did we find this number? By using this equation. V2 over V1 is 1 over 8, which is VR2 over VR1, and we found VR1 from this U1, which is 676.1. This one goes here, then VR2 can be found, that is 84.5125. Then we can use this VR2 to determine V2. What about U4? We can do the same. The compression ratio is 8. That means V4 divided by V3 is also compression ratio R, which is VR4 divided by VR3. So this one is 8. And can we find VR3? Yes, at 2200 Kelvin. So let's find VR3 at 2200. At 2200 Kelvin, VR2 is 2.012. So this is 2.012. Then we have everything. Can you determine VR4? Now, yes. So from this, we can determine VR4. So basically 8 times 2.012. So the answer is 16.096. If you know VR4, can you determine U4? Yes, from the same table. Let's find 16. 16, not here, 16.096 is between these two numbers. So we can do linear interpolation to determine U, which is between these two numbers. So if you do a linear interpolation, you can find U4, which is 897.3 kilojoule per kilogram. Okay? Of course, this table A22 is going to be provided in the final exam. So once you got here, then it's almost done. there's one more thing, which is the mass of the system. So can we determine the mass? Yes. By how? If you want to determine the mass of the system, we can use ideal gas for air. PV is MRT. Where can you apply this PV MRT? At state number 1, 2, 3, 4. It's going to be the easiest when you apply this at state number 1, because we know P1, T1, and V1. T1, V1 is MRT1. T1 is 1 bar, which means 100 kilopascal, and V1 is 400 centimeter cube. 400 centimeter cube. So 400 divided by 110,000 meter cube. No, 1 million, right? Yeah. And gas constant R is going to be 0.287 kilojoule per kilogram Kelvin. This is for air. And temperature T is 290 Kelvin. So we have everything. Can you determine the mass? Yes, the mass of the system is 4.806 times 10 to minus 4 kilogram. So we got the mass, U1, U2, U3, U4. So we have everything. So let's solve this problem. What is the heat addition? We can go back to this energy balance equation. Where is the heat addition? Heat addition is Q23. So we can calculate Q23 by mass times U3 minus U2. Heat addition Q23 is going to be mass times, what was it? U3 minus U2. U3 minus U2. And we know the mass here, 4.806 times 10 to minus 4. Do we know U3? Yes, here, 1872.4. Do we know U2? Here, 475.11. So can you determine Q23? Yes, Q23 is going to be 6715 kilojoule. So this is the heat addition to the system. Then what is the net work? The net work can be determined by, so now this time, B net work can be determined by the work produced between 3 to 4 and minus the work consumed between 1 and 2. This is the expansion process. This is the compression process. We produce work when we expand. We consume work when we compress. So this is Q3 and W34 minus W12. So what is W34? W34 is going to be mass times U3 minus U4 minus W12. Here, mass times U2 minus U1. We have the mass U3, U4, U2, and U1. So we have everything. Can you determine W net? Yes. W net is 0.3397 kilojoule. Then what is the next? The thermal efficiency. How do we determine the thermal efficiency? The desired output, in this case, net work thermal efficiency is net work divided by heat transfer in, which is this one, Q23. So this is 0.3397 divided by 0.6715. So the thermal efficiency is going to be 0.506. So about 50.6%. So mean effective pressure, the equation is mean effective pressure can be determined by net work divided by V1 minus V2. So the net work is 0.3397 kilojoule divided by V1 is 400 centimeter cube minus V2 50 centimeter cube. So we get 9.71 bar. Okay, so that's how you complete air standard analysis for this Otto cycle. So this is a typical problem you can expect from the final exam. Any question? Yes. Oh, that should be meters cube. And also, you know, when you calculate that you get kilopascal, you need to do a unit conversion here and there. You don't have to calculate this one in bar. You can use, you know, you can say 971 kilopascal. Of course, this is a very basic analysis. The actual analysis on a gasoline engine is too complicated because and therefore we rely on computer simulation. So this is just, you know, for a very simple comparison when you have, you know, the multiple Otto cycles to compare. Again, you know, we are not studying engine. We are studying how we can use thermodynamic equations for various applications. This one is going to be Otto cycle. Any other question? No? Okay, then let's go to the next cycle, which is diesel cycle. There's not much difference between Otto cycle and diesel cycle. The only difference is going to be between 2 and 3. So let me show you the difference between Otto cycle and diesel cycle. Process 1-2, isentropic compression. Process 1-2, isentropic compression. They're the same. Process 3-4, isentropic expansion. Isentropic expansion, they're the same. Process 4-1, constant volume heat rejection. Constant volume heat rejection, they're the same. The only difference is how, you know, the combustion process. For Otto cycle, we assume that it is constant volume heat addition, which makes sense because the combustion takes place by a spark plug. It's going to be just one brief moment when we can assume volume is almost constant. On the other hand, in diesel cycle, we rely on self-ignition due to high pressure, so it's going to be spontaneous, you know, the combustion, you know, all over the places. So we assume that the pressure remains constant. So process 2 to 3 is going to be constant pressure heat addition, while Otto cycle has constant volume heat addition. So that's the only difference between these two. Then, how can we come up with PV and TS diagram? So left-hand side, we have PV diagram. The right-hand side, we have TS diagram. The starting point is always the same here. Number one here, number one here. And now we have an isentropic compression. So the volume should decrease. Pressure should go up because it's a compression process. So process 1 to 2 is going to look like that. 2. On this TS diagram, it's going to be isentropic compression. So entropy should remain constant. S1 is the same as S2. Since it is a compression process, temperature should go up when you compress a working gas. So process 1 to 2 is going to be this way. So there's number 2. Process 2 to 3 is going to be constant pressure heat addition. It's not constant volume anymore. So where is pressure? The vertical axis. So P2 should be the same as P3. And constant pressure heat is added. When pressure remains constant, heat is added. Therefore, volume goes up. This way. Number 3. What about on this TS diagram? So it's a constant pressure heat addition. Heat is added, therefore temperature goes up. It is waste, form of energy. So waste is added to the system. Entropy should increase because entropy measures how much waste you have, right? So entropy should go up, temperature should go up. This way. Number 3. Number 3 to 4, isentropic expansion. So entropy remains constant and it's an expansion process. Volume should go up, pressure should go down. This way. Number 4. What about on this TS diagram? It's an isentropic. Entropy remains constant. Expansion process, temperature should go down. Entropy remains constant. S3 is the same as S4. And temperature should go down because it's an expansion process. Finally, we have constant volume heat rejection. Constant volume. V remains constant. Heat is removed. Therefore, pressure should go down. This way. V4 is the same as V1. In this case, it is removed. So waste energy is removed from the system. So we have a less waste. So entropy should go down because entropy measures how much waste do you have. More waste, more entropy, right? And it is removed. So temperature goes down. Temperature goes down and entropy goes down. So this way. So there's a PV and TS diagram. Again, we have the same compression ratio. When the piston is bottom dead center, when piston is top dead center. So V1, V2, the ratio between V1 and V2 is the compression ratio. So the compression ratio is called R, which is V1 over V2. Okay, I get that, but there is one more parameter for EGR cycle because we have one more volume, V3. The ratio between V2 and V3 is called cutoff ratio. Cutoff ratio, R of C. This cutoff ratio can be determined by V3 over V2. So this is the only new thing. Okay, that's it. How can we determine the energy balance equation? Of course, everything should be the same except process 2 to 3. So everything should be the same. except process 2 to 3. So except this one, everything should be the same. And U2 minus U1 is W12. W34 is M U3, excuse me, U3 minus U4. And Q41 is going to be mass times U4 minus U1. So everything is the same except process 2 to 3. Why? Because process 2 to 3 is constant pressure process. So let's go back to this energy balance equation. Where is constant pressure process? This blue one. So we are going to use this one. So it's a constant pressure heat addition. Heat is added when pressure remains constant. So the equation is going to be Q in. It is process between 2 and 3. Q to 3 is mass times between 2 and 3. H3 minus H2. That is the energy balance equation. The last one. Here's my blue. Oh, right here. Mass times H3 minus H2, which is Q23. So this is the only difference between the Otto cycle and this EGR cycle. How can we improve the performance of this EGR cycle? The same thing. The piston looks like this. This is the top data center. This is the bottom data center. We just need to compress more up to here. So we can add this much by increasing the compression ratio. But we couldn't do that when we had Otto cycle because it's a spark ignition system. But this one is a EGR cycle. It's a compression ignition system. So we can compress more. So R value for EGR cycle is usually much higher than R value in Otto cycle. That's why EGR cycle is more efficient than Otto cycle. Okay? So here's a summary. So the advantage, the simplest way to improve this reciprocating internal combustion engine is to have high compression ratio. High compression ratio. However, since the temperature of the fuel-air mixture being compressed in spark ignition system, which is a gasoline engine, you cannot compress too much. Then it will, the self-ignite. So we cannot have high compression ratio in a spark ignition engine. Otherwise, it will go auto ignition, or which is called knock. On the other hand, diesel engine, which is compression ignition, we don't have air-fuel mixture. So the main difference between Otto cycle and diesel cycle is that we have air-fuel mixture in the system. So if you compress more, then the undergo compression process and when high pressure. So you cannot increase R too much. But in EGR cycle, we only have air in the system. So if you compress more, what's going to happen? You have to compress the air. Nothing wrong. So you can compress more and more. And when it is at the highest pressure, then you inject fuel. Then it's going to, undergo self-ignition. So that is called compression ignition system. So in this case, R can go high, no problem, okay? That's the main difference between these two. Simply, you mix them, air and fuel, and inject into the engine, which is simple. However, to improve the compression ratio, you don't mix them, just inject air and then compress as much as you can. And when it is right the time to have an ignition, then you inject fuel in the system so that we can have high compression ratio. Of course, this one is more complicated, more expensive, but has higher efficiency because of this IR value. Okay, that's everything. Let's practice a problem for this diesel cycle. That will be all for today. So actually this air standard analysis is pretty simple because there's only one table that you are going to use. The ideal gas properties of air, table A22. So in this case, what we are going to determine? We are going to determine U1. Where is the energy balance equation? Where are you? Oh, energy balance equation. Don't be shy. I lost it. That's weird. I just wrote it. Oh, here. So the energy balance equation, the problem is this H2 and H3. So we are going to find H2, H3, and the other properties are going to be U. But you don't have to find U1, U2, U3, U4, H2, H3. You just need to find U1, U2, and I'm sorry, not U2, U1, H2, H3, U4. So these are the four thermodynamic properties that you are going to find when you have this diesel cycle. So U1, H2, H3, and U4 is the one that you want to determine. So let's do that. Whenever you have air standard analysis, I told you that please make TV and TS diagram, which is very simple now because we did many times today. So we are starting from here. 1, 2, 3, 4. So we have TV diagram, TS diagram. 1, 2, 3, 4, and back. 1, 2, 3, and 4. This one is constant pressure process, so P2 is the same as P3. V1 is the same as V4. S1 is the same as S2. S3 is the same as S4. Okay, so let's find them. The pressure at the beginning is 95 kilopascal. So this one is 95 kilopascal. And temperature, T1 is 300. Okay, we have temperature. When you know temperature, you can find U1, no problem. So temperature, T1 is 300 Kelvin. That's good. And at the end of the heat addition, so heat addition is between 2 and 3. So at the end, 3. So temperature and pressure at 3 is 7.2 megapascal. Okay, so these two are 7.2 megapascal. And the temperature here is going to be 2150 Kelvin. So T3 is 2150 Kelvin. So let's find the simplest ones first. Which one? Where's my tape? U1 and H3. U1, the temperature is 300 Kelvin. So if you go to table A22, there is 300 right here. And we want to find U 214.07. 214.07 kilojoule per kilogram. What about H3? 2150. 2150. 2150. What is H2? H is this one. 2440.3. 2440.3 kilojoule per kilogram. Oh, we already found 2 out of 4. Things are going very well. I like that. Now let's find H2. How can we do that? I told you that when you have an isentropic process, we can use this equation. V1 over V2 is VR1 over VR2. Similarly, you can use P. P2 over P1 is PR2 over PR1. Wait, we know P1, 95 kilopascal. We know P2, 7.2 megapascal. Okay, so this is the one that we are going to use. So let me write it here. P2 over P1 is PR2 over PR1. So what is P1? 95 kilopascal. What is P2? 7.2. 7,200. Do we know PR1? We do not know, but we know temperature. So let's find PR1 at 700 kilopascal. At 700 kilopascal, PR is 1.386. 1.386 at 300 Kelvin from table A22. Then we have everything. Can you determine PR2? Yes. PR2 is going to be 105.04. So let's find H2 from PR2. 105.04. So where is 105? Oh, time is over. Let's find 105, okay? 105, where are you? 105 is between these two numbers. So can you find H? Yes. By how? By linear interpolation. Then you get 1022.82. 1022.82 kilojoule per kilogram. This one is 8 at this one from table A22. Okay? So let's stop here. And on Thursday, we are going to study how to determine U4. That will be all. And then we can determine each answer to each question. Okay? That's all for today. Any question? No? Then see you on Thursday. Thank you.